So in this video, we'd like to discuss conjugate acid-base pairs and the Bronsted-Lowry definition of acids and bases. In the old definition, Arrhenius definition, an acid was simply something that supplied H plus or H3O plus in water solution, and a base produced OH minus. But the base produced OH minus by direct dissociation. So sodium hydroxide, for instance, would dissociate to form sodium and hydroxide. It contained the hydroxide. With the Bronsted-Lowry definition, the acid is a proton donor, the base is a proton acceptor. The base can be a substance that doesn't contain OH minus at all. And we've seen already ammonia can accept a proton from water and become NH4 plus, leaving the water as OH minus. So it's a different way of producing a basic solution. But this idea has to be fleshed out a little bit. There's conjugate acid-base pairs is a very useful concept, and it leads to a whole other class of weak bases besides the amines that we're already familiar with. So let's get started, and let's look at our original example of just the weak acid, acetic acid. So here it is, the equilibrium that we always write for the dissociation of acetic acid, and clearly acetic acid is giving up a proton to water to produce H3O plus and leaving CH3COO minus. That's acetate. Okay, so according to Bronsted-Lowry, the acetic acid is a Bronsted-Lowry acid. It's donating a proton. Interestingly, water is behaving as a Bronsted-Lowry base here. Okay, it is accepting a proton, so that makes it a base. In Arrhenius view, you would never think of water as a base, but here it is. Okay, and moreover, if you look at it from the other side, the reactions, this is an equilibrium, and we're looking at reactions that go in both directions. If you look at the reaction going from right to left, H3O plus is donating a proton to acetate. So in that case, H3O plus is an acid and acetate is a base because it's accepting that proton. Okay, so you have within the one equation two pairs that are called conjugate acid-base pairs. Okay, CH3COOH and CH3COO minus are a conjugate acid-base pair. And you can tell they just differ by one proton, right? You take the acid and pluck up H plus off of it, you get the base of the pair. And likewise, H3O plus and H2O are a conjugate acid-base pair also. Okay. We can do the same thing with the ammonia reaction. Okay, this we've studied already and looked at in quite some detail. But here now the base is ammonia. It's accepting a proton from water. Water is acting as an acid here. Okay, so Bronsted-Lowry acid, water is donating a proton to the Bronsted-Lowry base, ammonia. And that produces OH minus and NH4 plus. But if you look at the reaction going backwards, that would be a proton being donated from NH4 plus, the ammonium, donated to OH minus, which is acting as a base in that direction. So here, NH3 and NH4 plus are conjugate acid-base pair, and H2O and OH minus are a conjugate acid-base pair. Okay, and again, they just differ from each other by a proton. And it's kind of interesting also, you notice that in the acetic acid reaction at the top, water is behaving as a base, but in the ammonia reaction, water is behaving as an acid. Some compounds can do that. They can behave either as a base accepting a proton or as an acid donating a proton. They're called amphoteric, just for a vocabulary word. Water is an amphoteric substance because it can do both of those. So one other thing to reiterate here, how do we write these reactions? We have to remember if someone asks you to write acid, gives you a weak acid and says write the acid dissociation equilibrium for this weak acid, you put it with water and then you transfer the proton. If they give you an acid, the proton gets transferred to the water, away from the acid. And the base, you put it with water and transfer the proton also, only this time though it's away from water and to the base. So in each case, you put the substance with water and transfer the proton in the appropriate direction. And we're going to need to remember that. But I want to talk a little bit about acetate here. Okay, it's the conjugate base of acetic acid, acetate. All right. Now, question. Is that just sort of an abstraction, calling it a conjugate base, or is it really a base? I mean, if you dissolve acetate in water, do you get a basic solution? How would you even do that? Okay, how would you? Well, you can do that, and it is basic. The way you do it is with a substance like this, another compound that contains acetate. Okay, sodium acetate's a great example. It's a white solid, very soluble, cheap compound, and it dissociates into sodium and acetate ion in solution. The sodium, as usual, doesn't do much, and then but you also have the acetate in water solution, aqueous acetate. Okay. And the question is then, does it really act like a base? Does it produce a basic solution? In other words, is a solution of sodium acetate basic? And the answer is yes, absolutely it is. In fact, you can treat that acetate just exactly the same way as we treated ammonia. Okay? You can write the base dissociation. How would you do that? Put the base with the water, transfer the proton in the appropriate direction. So here it is, right? I put the acetate, put it with water, transfer the proton. That means the base acetate is getting a proton from the acid water. It's just exactly analogous to the ammonia reaction we've looked at already quite a bit. And what happens, of course, the water has become OH minus because it gave up a proton. And look, you've actually produced some acetic acid, okay? Now you think, well, doesn't that make it an acidic solution? Well, no, I mean, that's an undissociated acetic acid. What makes the solution at the top acidic is the H3O plus, not the CH3COOH, right? This solution down at the bottom is basic because of the presence of OH minus. And it does contain a small amount of acetic acid, CH3COOH, that was formed from water transferring a proton to acetate. We can also write Kb for this, just like we wrote Kb for ammonia. There it is. Products over reactants, OH minus and CH3COOH are the products. Of course, leaving out the water, and on the bottom you have CH3COO minus. Okay, so you write Kb just in the same way as before. Now, we'd like to go ahead and do a problem where we calculate the pH of a solution of sodium acetate, and that would be a base problem. And by the way, in this equation that I've written, sometimes students want to ask me, what happened to the sodium? Well, the sodium is just a spectator. I could put a sodium ion on both sides of this equation. It's in the solution, but there's no need to necessarily write it in the reaction because it's just a spectator, and it's be Na plus on both sides of this equation. But then, see, if we want to do a problem where we calculate the pH of an ammonia solution, only now calculate the pH of a acetate solution, we need the value of this Kb. We need to know a number, just like for the acetic acid solution, you needed to know Ka. Well, now we need to know Kb, right? But it's not in the book. You look in the back of the book, and it's not there. The reason why is because everyone, after they've taken General Chemistry 2, knows how to calculate it from the Ka for the conjugate acid. So let me write that down. We can find the pH of an acetate solution just in the same way as we did an ammonia solution. Same ice table, same everything. Okay. However, we need Kb, and the value of Kb is not listed in most books. Here's how you find it. First, acetic acid. Here's Ka, right? Now here's the base dissociation for acetate, and here's its Kb. What I want to show you is, look what happens when you multiply the two together. Here's the Kb, I'm sorry, that's the Ka, isn't it? Here's the Ka multiplied by the Kb. And you notice the first one's got acetate in the numerator and the other's got acetate in the denominator. The first one's got acetic acid in the denominator and the other one's got acetic acid in the numerator. So they can all cancel out, and what you wind up with is H3O plus times OH minus, which we recognize as the expression for Kw, the autoionization equilibrium constant, and we know its value. Its value is 10 to the minus 14 at 25 degrees. Okay. So Ka times Kb for a conjugate acid-base pair, Ka times Kb is Kw. So in this case, we'd like to have Kb for acetate to do a problem with that, but we don't know it, but we do know Ka for acetic acid, so we'll be able to figure it out. So let's do a problem like that. Find the pH of a 0.22 molar solution of sodium acetate. And then it gives you Ka for acetic acid, 1.8 times 10 to the minus 5. Okay? So the first thing we got to do, let's find that Kb. It is the conjugate base of acetic acid, and Ka for the acetic acid is given, so simple calculation. Okay? 10 to the minus 14 divided by 1.8 times 10 to the minus 5. It's 5.56 times 10 to the minus 10. I should mention that 6, that's subscript 6. It's not actually significant here, but since I'm going to use it, it's an intermediate result, and I'm carrying an extra digit. So that 6 is the extra digit. But also, 10 to the minus 10, okay? That's not a big number. Kb for acetate is very small. That means it's a rather weak base, okay? That means it's a weak base. But now we go ahead, what do we need? An ice table, right? Actually, maybe we don't need an ice table because we've done this same calculation so many times that maybe now we don't. But okay, initially 0.22 molar solution of acetate, and pretend no reaction has happened yet. Initially, OH minus is 0, and the acetic acid CH3COOH is 0. Change line, minus X on the reactants and plus X for each of the products. Then the equilibrium line, just add up the previous two lines, 0.22 minus X, X, and X. And those have to go into the expression for Kb. So here's the expression for Kb. It's X squared then over 0.22 minus X. And we need to consider, as usual, that would be a quadratic, but we consider the X is small approximation. With a Kb of 10 to the minus 10, this reaction doesn't go very far. That means X is going to be very small. I almost don't need to do the check to be able to see, but you know, we always do it. But let's just see, if the X is small approximation is good, then it's neglected in the denominator. You have Kb equals X squared over just 0.22. Multiply both sides by 0.22 and take the square root. You get X is 0.22, is the square root of 0.22 times Kb. Put in the numbers, it comes out 1.1 times 10 to the minus 5. Now this is a base problem, so that is the value of the hydroxide ion concentration, something times 10 to the minus 5. Is it indeed much less than 0.22? That's the check that we're supposed to run, right? 1.1 times 10 to the minus 5. Well, that's really much, much smaller than 0.22. So, right, if you took 0.22 in that denominator and subtracted 1 times 10 to the minus 5, you still got 0.22, right? So But clearly, this is much less than 5%. So that's not what that question asked us. They asked for the pH of this solution. We have the OH minus concentration. So first let's calculate the pOH by taking the negative base 10 log of the OH minus concentration and then subtract that from 14. Okay, so pOH is negative base 10 log of 3.3. Oops, I got the wrong number in there, don't I? I forgot to, I think the next number is right. I was working on a previous problem and I have the wrong number. It should be the negative base 10 log of 1.1 times 10 to the minus 5 is 4.95. And you subtract from 14, you should get 9.05. I just have the wrong number in the brackets there, my mistake. But let's do another one. This is a little bit more complicated on the front end, but everything else is very similar. Find the pH of a 0.52 molar solution of sodium nitrite. What is that? Well, I'll tell you. Sodium nitrite is NaNO2. Of course, you know nitrate is NO3. This is NO2. It's a soluble substance. So when you dissolve it, you get sodium and nitrite, okay? But that nitrite is the conjugate base of the acid nitrous acid, okay? Now, how do you, if somebody gives you a base, they say, what is the conjugate acid of this substance? You put a H plus on it, right? So the conjugate acid of NO2 minus would just be HNO2. That's nitrous acid, okay? So nitrous acid is the HNO2 is the conjugate acid of NO2 minus, okay? Now, we need the Kb of NO2 minus, right? It's the base, nitrite, just like acetate was the base in the previous problem. NO2 minus is the base here. We find the Kb, Kw over the Ka of the conjugate acid, which was given in the problem. You wind up with 2.17 times 10 to the minus 11. Again, wow, very small Kb, right? So this is not a very strong base at all. In fact, it's weaker than the previous one, so we expect to have a somewhat a lower pH, right? Higher pH would mean strong base. But anyway, let's see what happens. Here's the ice table. Like I say, we almost don't need it. It looks very similar. Instead of 0.22, we've got 0.52. Here's the Kb. Again, X is small, ought to work great because we have a Kb that's very, very small. Let's check. X is 0.52 times Kb. It turns out to be 3.36 times 10 to the minus 6. Now you know where I got that from on the previous slide. That I had the wrong number in there for that. But that's the OH minus ion concentration. You do your check. It's way less than 5%. And the pH comes out to be 5.4. That's the pOH, 5.47. And that makes the pH 8.53. Okay. So it is a little lower. It is a weaker base than the previous problem. So that's the way you do those. We can also do analogous problems with these last two. Those are called basic salts. Not basic as in fundamental, but basic as in not acidic, right? They're basic salts, and that's how you do those. You can also have acidic salts, and there's also a few other things to tell you about conjugate acid-base pairs and their relative strengths and things like that. Not too tough, but this is the basic kind of this is the kind of problem that you can run into with these. And you got to practice them a little bit, so we'll do some of that as well. But anyway, more to come on conjugate acids and bases.